Hello, and welcome to our monthly webinar where we present to you the latest and greatest CAD and CAE software capabilities. My name is John Dow, and I'll be your new ANSYS Applications Engineer. Here at KETIV, where we empower today's innovators for a better tomorrow. In last month's webinar, we went over Ansys Discovery Live Mechanical, where we performed on-demand simulation for static structural problems. If you missed this webinar, please subscribe to our channels to watch the past recorded webinars. For this week's webinar, we will be going over Discovery Live's ability to simulate fluid dynamics with our Ansys specialist, Tejas Rao. Before I hand it over to Tejas, we encourage you to interact with us by typing your questions in the Q&A fields. Tejas, would you like to introduce us to today's topic?
Thank you very much, John. Hi, everybody. Thanks for taking the time. My name is Tejas Rao, and I'm the manager of the Ansys Discovery pre-sales team based out of Ann Arbor, Michigan. So today we're going to talk to you about how you might be able to use Discovery Live for fluid dynamic simulations. But before we get into the detailed demo, we do want to go into a few slides just to remind the audience how the Discovery technology fits in with the overall ANSYS portfolio. So with that, why don't I jump into the slides, and then we'll go into the demo. And then, of course, at the end, we'll have a Q&A session where I'll be happy to answer whatever questions you guys might have. OK, so let's consider a design engineer who has an idea. Right? Today, the design engineer sends that idea over to an expert analyst or a consultant and waits for results to come back. And this loop for most medium to large size companies typically can take 1 to 3 days. Now, this design engineer, she has tons of ideas. And if she has to do this for every single idea, it might take weeks to use traditional simulation to evaluate all those designs, which of course is not ideal. Now, if you consider that this design engineer is just one out of many, the potential slowdown in the product development cycle is quite significant, right? So this is something that we're trying to address with the Discovery technology. Now, look at this another way. Let's say you have your typical product development process where you're going from left initial design to the right for an optimized and validated final model. Each of these circles represents a design idea, and today, companies rely on a single expert analyst or maybe an outside consultant to evaluate all these design ideas. But this poor analyst only has so much time in the day, which means that many design ideas go untested. And this, of course, reduces the innovation that your company can take advantage of. So what if the design engineer could use Discovery to evaluate some of these early design ideas and identify the best candidates to move down the road and have the expert analyst look at for, in more detail using ANSYS flagship tools. This is exactly what we're trying to do with Discovery. And this is how we see Discovery fitting in to the product development process. It's a tool which is designed for design engineers. It's intended for design engineers to use early in the design cycle. And, really the key benefits of Discovery that you don't get anywhere else are instantaneous real-time simulation, the ability to solve multiple different physics disciplines. Of course, today we're going to talk about fluid flow, integrated 3D modeling, and of course, ANSYS technology under the hood. So simulation for every engineer is what we're trying to do with Discovery. And today we're going to talk about this in the context of fluid flow simulations. OK. So with that, let me get out of slideshow mode and let me jump into Discovery Live. So what you're seeing is Discovery Live version 19.2, which is the current version we have on the market. And what I want to do over the next 20 to 30 minutes is just show you a variety of examples of fluid flow simulation. Okay, and the purpose here is just to trigger in your mind how you might benefit from using this technology in your product development process. Okay, and then of course, once you think about this and you want to know how you guys can use it, contact our colleagues at KETIV, and they'll be more than happy to discuss your individual applications with you. Okay, so let's get started. So I'm going to start off by bringing in a model which looks like this. It's a generic model, and you might have seen these animations before. I just want to walk you through it. So here I have a generic truck of some sort, and this is early on in the design cycle. And let's say you're an industrial designer who wants to understand what the overall flow field around this vehicle looks like. Remember, you're not interested in predicting accurate drag or accurate lift. That comes later down the product development cycle. Right now, you want to understand the flow features around it, and make design changes if they're necessary. Okay. For a model like this, using traditional techniques would take, I would say, easily 2 to 3 days, or maybe even longer, depending on how busy the expert analyst is. But what if you could do something as simple as this? Create solution, choose fluid flow, say it's an external flow, specify the direction the wind is approaching the vehicle, specify the ground plane, which is the road, and in just a few seconds, you have your simulation starting. What I'm showing you here is not pre-recorded or pre-solved. Everything that I did to set up and run the simulation, you saw me do in the last 30 seconds. It is indeed that fast. This is what Discovery Live brings to you: instantaneous, real-time simulation. Okay, so let's say the goal of this simulation is to understand the flow structure behind the cab around the bed of the truck. Maybe this truck is designed to carry fine sand particles or something like that, and you don't want the flow to be very turbulent in the yellow bed area right in here. So as an industrial designer, you might look at this and say, okay, I can see what's going on. I think I need to put some kind of deflector on top of the cab to see if that will make a difference. So I already have the deflector modeled up, and I can just turn that on. Oops, it didn't get turned on. I can just turn that on, and you see the solution responding immediately. Once again, this is happening in real time on my computer. This is not pre-solved. So in just a few seconds, a designer is able to look and say, you know what, I can put a deflector which looks roughly this shape and roughly this height, and I'm able to get the flow to go all the way over and around the cab or the bed of this truck. So if you accomplish this, you basically saved your company days of time to be able to get to this point. Now, once the designer is able to use this information to create an initial design, then they pass it on to the expert who does a high fidelity, high accuracy simulation using ANSYS CFD and provides exact values of drag, lift, and so on and so forth. But being able to cut several iterations out of the loop early on is a significant business benefit. Okay, let's take a look at a couple of other things. Okay, what if I wanted to visualize the streamlines around this vehicle? Okay, and the goal here is to take a look at that side view mirror. Okay, this guy right there. Okay, so let me mess around with this a little bit. Okay, that looks good. What I'm really interested in is this really turbulent flow structure immediately behind the side view mirror or the rear view mirror. If I look at it from this angle, you can see what I'm talking about. Okay, so this is really bad, and if I move to the other side, you see the same thing. Okay, so the design engineer might want to know what happens if I just change the angle of this mirror a little bit. Okay, and I can do that very easily using our built-in direct modeling tools. So I'm just going to rotate this mirror, maybe reposition it slightly, maybe like that. Here you go. And right away, you see that the flow field is a lot smoother. Now, those of you who are familiar with this kind of stuff, you might say, well, that's pretty obvious. But there are a lot of engineers who are not sure how their design is going to respond to changes in the geometry. And this tool is intended to give them that insight. So if I move the streamlines over to the top, you can see the very turbulent flow structure, which is the original shape or position of the mirror. And then look at the bottom, much more streamlined, right? So this is how we foresee a lot of engineers using Discovery, Discovery Live. Okay. Now, I just want to show you something kind of cool. What if you're in a design review meeting with your client and the client says, you know, this is all well and good, but our trucks travel in a convoy. There's going to be 2 trucks, maybe they're autonomous trucks or something like that, traveling right behind one another. Can you tell me what the flow field will look like around the second vehicle? Normally, if somebody asks you this question, you go away, come back a week or 2 later after having done a detailed simulation to show the results. But what if you could do something like this, where you literally just duplicate the vehicle like that, and now the software is solving for both? I think you guys get our point, right? Being able to do this kind of instantaneous simulation to evaluate design direction and give you design guidance is a very, very useful thing. And for the first time, ANSYS has invented a technology which allows you to do just that. Okay. Now, of course, this is a rather extreme example of a truck, and most of you in the audience might say, you know, we don't design trucks, so this is kind of a useless, cool, but maybe useless example. And maybe I'll agree with you. So let's take a look at something a little bit more realistic or applicable. Okay. So I'm going to open up a new geometry here, and let me find it. There we go. By the way, I want to point out that you can import geometry in pretty much any format into Discovery Live. You can see all the native formats from all the major CAD systems, but also all the different types of neutral formats like Parasolid, Step, JT, STL, and so on. Okay. So I'm just going to do a little filter on my search, and let's use this one. Okay. So what I have in this application example is I have a duct system. Okay. And in this case, I have an inlet, which is located over there, and I have 2 outlets over here. Okay. And the design brief for the engineer is to make sure that the flow is as uniformly split between the top and the bottom outlets as much as possible. Okay, the position of these outlets are fixed. So that position is fixed, this position is fixed, and the inlet is fixed as well. So the engineer is not able to change those locations, but they're required to design a duct which splits the flow evenly between the top and the bottom. Okay, so the engineer has created the simplest possible shape and wants to know if this design is sufficient to be able to achieve that design goal. Once again, using traditional simulation techniques, this might take several hours, but what if you could do something like this? We say fluid flow. In this case, we want to do an internal flow. We specify this to be the inlet, this to be the outlet, and this to be the other outlet. And with that minimum specification, I see my flow starting to develop instantaneously. Now it assumed a 0.5 meters per second inlet velocity. You can change it to whatever you want. And of course, you can also change it to many of these different types of boundary conditions, like you could have done a mass flow rate inlet, a pressure inlet, you know, what have you. Let's take a look at this in a cross section. Okay. And you know, you can obviously see that most of the flow is going to the bottom. I mean, for those of you who are familiar with fluid dynamics, this might not come as a surprise to you. Okay, but maybe something that you want to do is actually evaluate what that what the flow rates are at the top and the bottom. Okay, so let's just create a monitor, and in this case, I'm going to do integral of velocity. Okay, on this face. Okay. And let me just look at that. By the way, guys, please ignore the units that my software is throwing out. I have a slightly non-standard version of the tool. Okay, and I'm going to make a second duplicate one. So I'm going to duplicate this calculator, and I'm going to edit its location, and I'm going to say, here we are. Okay, and in fact, I can rename this. So if I edit this, I'm going to call this outlet top, for example. And I'm going to call this outlet bottom. Okay. Once again, we're not trying to get precise, highly accurate values. We're just trying to get relative performance between A and B. Okay. So if I turn on the streamlines, for example, and it's pretty obvious what's going on, you can see most of the flow goes straight through the bottom. So the flow rate at the bottom is, a couple of orders magnitude greater than the flow rate at the top, right? This is what you see. Now, so you might ask yourself, what can you do to improve the design of this duct? Okay. So in this case, I actually have a couple of baffles already in place. So what happens if you put some kind of baffle in the middle, right? Like you see over here, okay? Obviously, you don't want to keep it straight up and down. You want to, tilt it this way to create some kind of splitter, okay? And that's exactly what we're doing. Once again, you can see the flow responding immediately to design changes. And you'll notice my design change is quite crude. This splitter kind of cuts right through the geometry. It doesn't matter. We're just exploring the design at the moment, right? And if I turn on my streamlines, you'll see kind of what's going on, right? You'll see that more flow is now being pushed to the top. And if you look at these numbers, you'll see that they start to, how do you say, get closer together, right? So let me do this. Maybe I want to change the shape of this even more, or change the orientation of this even more. So let me select that, and maybe I want to make it a little bit more curved like that. Maybe position it like this. And the instant I do that, look at these numbers, they start coming together, right? So as an engineer, I now know that having some kind of splitter makes the most sense. But now I'm thinking a little bit more detail. Maybe I don't want a flat splitter like this. Maybe I want a curved splitter like this, right? Is that going to be better in terms of making the transition between the top and the bottom more smooth, right? These are all ideas that design engineers often have early on in the design process, but are in most cases unable to evaluate them because it just takes too darn long to get these kind of simulation results, right? This is what we want to try to accomplish. Now, let's say we have one of those design review meetings and somebody says, okay, this looks good, but maybe we should try having, the baffle located over here, maybe like this, right? Or maybe even make a duplicate and move this guy over here. Is this a better situation than the other one, right? These are the kinds of results we're looking for. Okay, let me go to a slightly different example. You guys are mainly in the West Coast, maybe, so maybe many of you do electronics enclosures, right? So oftentimes when you're doing an electronics enclosure, the goal of the simulation might be to understand how to make the best use of the flow going through the enclosure, right? You want to make sure that most of the flow goes through the veins of this heat sink, which you see right over here. And you want to know if the location of your fan inlet, which is this, and these outlet slots are in a good position. Let's say you're trying to find that out. You're not looking at exact temperatures, but rather you're just looking at what can I do to improve the flow through the heatsink, because if I do that, I know that I'll have a good cooling performance. And then I can pass this on to the expert analyst for a more detailed evaluation of the actual temperatures that I'm getting, okay? So let's do that again. Create solution, fluid flow. In this case, I already have a generic shape which represents my enclosure, okay? And I'm going to specify a flow velocity. Let's just say 2 meters per second. I just made that up. And I'm going to specify these shapes as the outlet. Okay, so it's a pressure outlet. Sorry, let me do that again. Okay, there we go. Okay, That's all I need to do. And if I click play, you'll see once again the instantaneous stuff. You're probably going to get sick of hearing me say instantaneous, but that's what it is. Okay. So as you can see, this is a transient solution, so we can wait a little bit for the solution to settle down. You can see how the flow field is developing. You can take a look at the total time that the simulation has run, the real time of simulation on the bottom right corner. But very quickly, I can notice that most of my flow seems to be kind of going out through the top, and this is not really very good, right? I want to have more flow going through the veins of that heatsink. Okay, so let's just give this flow a second to develop. By the way, if you want to get more resolution, or what those of you familiar with simulation may call more mesh refinement, the setting is very simple. You just have this speed versus fidelity slider. So as I move the slider to the right, it'll take a little bit longer to solve, but you'll get your answer. You'll be able to capture a lot more geometry detail, right? Discovery Live, as has been mentioned in previous webinars of in this series, uses GPU technology from NVIDIA to be able to solve problems this quickly, right? So if you crank this fidelity slider to the right, it uses more GPU memory and resolves more geometry detail. If you move it to the left, it goes faster, but you capture less geometry. So, you have to figure out what setting is the best for you, but that's pretty much the only control that you need to worry about, right? Okay, so let's take a look at this. And if I look at it from the top, I'll see that most of the flow is going out straight through the top, right? So as a design engineer, you might say, well, I want to know what I can do to improve this, okay? So I'm going to go ahead and I'm going to create a block of some sort. So I'm going to create like a baffle, which is going to block the flow from going around in that direction, okay? And once again, I'm using our built-in geometry tools, but you certainly don't have to do that. You can use whatever CAD system you have to create these geometries, right? Now, just like before, the moment I put that in there, you can see how the flow is being blocked, right? See that? The flow is being blocked, and as a result, more flow is going through the top of this heatsink. So as a design engineer, this gives me a lot of guidance, right? Hey, maybe I shouldn't have my outlets here. Or if I do, maybe I need to plant an obstruction to kind of force the flow to turn right, Now, somebody else in your team might suggest something else. Maybe they want to let me zoom in a little bit so you can see better. Maybe they want to angle this this heatsink a little bit. That's an interesting idea. Can we create a cutout like that to capture more of the flow and have it go through the middle, right? And visually, you can see this idea seems to work. So maybe a combination of having that block and having the angled heatsink is a good solution for your particular design, right? So these are all ways we can see simulation being used with Discovery Live early on in the design process, just to get some idea of what's going on. And of course, today we're talking only about fluid flow, but you can couple this with thermal, structural model, and get a comprehensive idea of the performance of your design using Discovery Live. Okay, so I can pause this, make it not look like a bunch of worms, different types of post-processing ideas, right? So for example, I can do a composite 3D rendering. This is what this looks like. I can change the, this shows the high velocity regions, and you can see more clearly what's going on. You can see how more of that flow is going through here. Now, I'm not getting that much flow down the bottom. Maybe I can make some design changes to impact that as well, okay? Now, some of you may want to know what the flow field looks like inside, but maybe you have a natural convection problem, right? You don't have forced convection. So let's see how that works, okay? So I can modify this, or I can just do a new solution, and let's say fluid flow, and let's select this body again. Okay. Now with natural convection, I still have these outlets, let's say open to the air in this example. Okay, so let's specify a pressure. Okay, and I have let's say a very hot object here, some kind of transformer maybe, and I'm going to apply a heat flow boundary condition, maybe I don't know, 100 watts or something like that. Now all I need to do is specify gravity, or the direction of gravity. Okay, and let me make sure it's in the right direction. So it should be in the negative x direction. You can look on the bottom left, x is in the right direction. So minus 9.81 and then 0 over here, and then just click play, right? So as soon as I do that, let me turn this on. You can see the temperature plume starting to develop, right? Here we are. So you can see the hot air being heated by that cylindrical object, and you can see the plume rising up, right? So if you are designing some sort of maybe enclosed device, and you want to see where the hot air is likely to collect, so that you can put more sensitive components away from that location, this is an easy way to do it. Okay. And once again, it's just instantaneous, right? You just got to figure out how long you want to run the simulation, what fidelity to use, what boundary conditions to use, and have at it. Now, keep in mind, this is just the very first iteration of Discovery Live. This technology was released just in February of this year, and we're continuing to make improvements to it. But what you can do with just the first iteration is pretty amazing, in my opinion. Okay. Okay, excellent. I have one more example. Well, I actually have two more examples to show you. My next example, and by the way, these are all similar kind of physics that I'm showing you. I just want to show you as many different applications as I can to kind of stir the thoughts in your head. Okay. So in this scenario, I have some kind of heat exchanger. This is an EGR cooler. So we have an inlet of hot gas coming in there, and it's going out in this direction. Okay. Now I have a bunch of tubes in the middle, and you can see, of course, I have coolant flow coming in on the two top areas. And I know that having uniform flow distribution across all these tubes will give me better heat transfer. So as a design engineer, I just want to make sure, do I have that or not, right? So let's do that again, fluid flow. In this case, it's internal. So let's say this is my, my inlet. Let's say this is my outlet. And by now, you guys are used to this instantaneous stuff. You see this happening right away, okay? So let's take a look at it in cross-section. You can see what that looks like, okay? Let me bump up the velocities. Maybe this is, I don't know, 5 meters per second or something like that coming in from the inlet, which is air. By the way, this is all compressible. So if incompressible, sorry. So if you have compressibility effects, you may want to take that into consideration. And anyway, I can see right off the bat that my flow field is quite, how do you say, non-uniform. Most of the flow is going to the top. And there are many different ways I can visualize this flow field, right? There you go. I can look at it that way, or I can look at this with a composite view, which we talked about earlier. Many different ways to visualize the flow, okay? Now, judging by the results I see over here, I might decide to actually throw some vanes in there, okay? I'm going to throw some vanes in there, and you can see them designed in pink. And as soon as I drop them in there, and by the way, you could have had these already designed in your favorite CAD system. You just kind of turn them on and off. That's totally fine, right? You see what I'm doing, right? So I want to know if this is going to give me a better distribution, right? If I want to move some of these objects so that let's say I want to move this guy. I want to know what happens if I move this a little bit to the top. How is that going to change my flow distribution, right? Or maybe I need to move this a little bit closer to the bottom and maybe swing out the angle a little bit. I'm just making things up at this point, just to show you how the tool can be used to guide your design decisions. Maybe I don't need that vein on the top at all, the third vein, or maybe I need 4 of them. I don't know, right? These are the kind of questions design engineers ask themselves to be able to figure out what the best design candidate might be. And once they arrive at that design candidate, they pass it on to the expert analyst, who can do the high fidelity simulation to confirm and optimize the design. Okay, so this is the simulation on the hot side with the hot gases, but I actually have a similar simulation I want to do on the coolant side. So I'm going to do a new solution. Okay, and once again, this is an internal flow, and I want to say this is an inlet. Okay, and this is my outlet. And once again, instantaneous simulation, all good. I'm actually going to bump up the fidelity a little bit so I capture some of the details, the flow between those gaps. And if I take a look at the streamlines, I can see right away that just let me move these in to the right spot. I can see right away what's what's going on, right? So I just gotta position this just right here. There we have it, right? I'm just going to make this a little bit smaller. You can see, you can see what's happening to the flow. Most of the flow is kind of shortcutting and going straight from inlet to outlet. If I look at it from this view, and let me turn those pink veins off so they're not distracting. You can see that most of the flow is not getting into and around the tubes, right? This is obviously not good. And if I take a look at a cross-section view, let's see, like this, and if I look at it from this angle, you'll see most of the flow is kind of hanging around where you see the red areas, right? The middle section and the bottom right corner are not seeing sufficient flow, right? And this is not good. So I want to know, can I create some baffles to kind of force the flow to do something different, right? So once again, I'm going to use my my built-in geometry tool, okay? And of course, you can do this with your own favorite tool. Of course, I'm going to just create like a baffle, which looks like this. And you can see I can be very crude about this, right? I can just make it, do whatever I want. So if I take a look at the flow now, oh, I just got to do one more thing. You can see that the moment I turn it on and make the flow aware of the blockage, you'll start to see the flow field having to bend around that that obstruction that I made. So what this is telling me is that my my design idea of having this object kind of as a baffle to force the flow to go around allows me to make a much more efficient use of the tubes through the heat exchanger, right? Once again, just design exploration to allow you to think of ideas, evaluate it in seconds, and then use this knowledge to make a detailed design in your CAD system, and then send it over to the expert. Okay. So that's pretty much it, guys, in terms of my demonstration. Hopefully, I've shown you many examples of how we think Discovery Live can be used in the design process. And this gets you thinking more about how you might use this in your applications. Okay. So with that, why don't I pass it back to my colleague John, John, we can take questions. If you could read them out to me, that would be great. I'll be happy to answer them as best as I can in the given time.
Okay, sure. So one of the first questions that we have about the PC specifications that are required to run Ansys Discovery Live.
Okay. Yeah, absolutely. So I think the question is, what kind of machine is needed? And this is a very, very good question. In order to run Discovery Live, you need a NVIDIA GPU. This technology is based on the NVIDIA CUDA technology. And you need an NVIDIA GPU with a minimum of 4 gigabytes of dedicated video memory. Okay. I'm using a P5000 NVIDIA card, which has 16 gigabyte of dedicated video memory, which is really cool. If you can get that, that's awesome. But one level below, for example, a P4000, you have 8 gig, or one level below that is 6 gig. Those are all great types of cards you can use. Okay. If you're like a one-man consulting shop and Quadro cards are a little bit expensive, the consumer grade GeForce will also work, but of course we recommend the Quadro cards. So NVIDIA, minimum 4 gigabyte dedicated video RAM. That's what you need to worry about.
Okay, the next question is in terms of internal and external flow. We saw you do internal flow. Are you capable of doing internal and external flow in one analysis?
Yeah, you certainly can. I mean, if you have a situation where you have a flow approaching an object and part of it goes inside and the rest goes around it, that's certainly possible. One thing you have to consider is that the only control you have in terms of geometry fidelity is this slider bar. And the slider bar, the amount of fidelity you get also is based on the power of your GPU. So if you have a very complicated shape with a large size but very small flow features that you're trying to capture, Discovery Live today would not be able to capture that. Okay, so we'd be happy to work with you through our colleagues at KETIV to help you identify if some of these situations might interfere with using Discovery Live, but there's no fundamental limitation on doing internal and external flow at the same time.
And the next question is, we saw you use multiple splitters to move the flow direction in different directions. Is it possible to collect the reaction forces of those splitters so you can do a stress analysis on the mechanical side?
Yeah, so these calculators that I used, we can do a variety of calculations. So you can see force in different directions and so on. I want to point out that the goal of those calculators is to help provide a quantitative directional guidance. You remember when I had the splitter with the duct and I was trying to get the even flow between the top and the bottom? The purpose of the calculator is to try to get a numerical value which shows me that the flow is balancing out. Of course, I can also look at it visually like I'm doing here. Okay, so the goal of Discovery Live is early in the design process is to provide you with guidance. So any numerical value that comes out of here, take it with that in mind, right? It's not going to be the precise value that you can use to get a very high fidelity answer for stress analysis. But if you want to get an approximate calculation of what the reaction forces are, for example, to use as an input into some other kind of simulation, certainly you can do that. Now, remember that it'll be an average over that entire surface. It will not be a distributed force. If you want to do that, we recommend that you go into a higher fidelity simulation, like Discovery AIM or something else.
Okay, and then the last question is, does Discovery Live support beam and shell models?
No, it doesn't. So first of all, the beam and shell question doesn't apply to fluid flow. I'm sure the person asking that question is aware of that. But from a structural simulation perspective, if you're doing beam and shell type simulations, we don't support that in Discovery Live. See, the main reason for using beam and shell, of course, as you guys know, is to get more efficient computation for certain types of geometry where you don't need to model the full solid, right? Now, efficiency of computation kind of gets thrown out the window with Discovery Live because it's so fast, even with full 3D geometry. Having said that, though, if you're doing a bridge or something like that, or a building, some kind of civil engineering application, beams would be better. It'll be even more faster. And if you're doing large fabricated sheet metals, then shell is probably faster, right? And you want to avoid those kind of applications for Discovery Live. Discovery Live is basically situations where you have solid geometry, meaning solid 3D geometry, not shells, beams, or zero thickness surfaces and stuff like that.
Okay, and I think that's it. That's all the Q&A that I have on this end.
So there we go. This is the last slide we have, and John, I give it back to you to close up.
Okay, thank you very much, Tejas, and thank you all for joining us today. We hope to see you in our next month's webinar, where we'll be going over Discovery Live's 3D design and concept modeling capabilities. If you are interested, please feel free to contact us for any free trials of the software. You could contact us through email or through the phone or through any of our channels. Okay, Tejas, I think that's it. Thank you all.
Thank you. Bye.